So we want to look at these four things. We'll be looking at real and virtual images, plane mirrors, curved mirrors, and images formed by curved mirrors. So we'll begin at real and virtual images. The real image is formed by the actual intersection of light rays. The light rays falling on an object, when they overlap or intersect to form this image, and it actually happens, we say a real image is formed. But if the image formed is not by the actual intersection of the light rays, or we only geometrically produce the light rays forward to an extent, just have an intersection somewhere, that is a virtual image. We see all this, no? So real images are formed by the actual intersection of light rays. Another one is that they can be cut on the screen. You can have them cast on the screen. Real images can be cut on the screen. You can have them pasted on the screen. Another one is that for real images, concave mirrors. Yeah. Concave mirrors produce such images, produces real images. Also, converging lens also do the same. Converging lens produces real images. Another thing is that real images are inverted. When we say inverted, that is upside down. For example, if you have an object which is an arrow, when a real image is cast on the screen, you have something that looks like this, inverted, upside down. So we have something like this, and something like this, passing through maybe a multiple instrument or something. So when you have something like this cast on the screen in which the image is inverted, it can be cut on the screen as you can see it, and it's actually formed by the intersection of light rays, or perhaps it's formed somewhere here. Either way. So we say a real image is formed. Now let's talk about virtual images. Virtual images. For virtual images, they are formed by they are not formed by actual intersection of light rays. It's a kind of manipulation that we do to get them. They are not formed by the actual intersection of light rays. Actual intersection of light rays. Another point is that they cannot be cut on the screen. That's why we say they are virtual. They are not real in the real sense. They are not real because we cannot see them visibly on the screen like real images. Real images can be noticed, can be seen, can be observed on the screen. But for real images, they are usually inside the optical instrument, inside the mirror, inside the lens. We cannot see them on the screen, being projected or pasted on the screen. So we have that they cannot be cut on the screen. They cannot be cut on the screen. Another thing is that diverging lens and plane mirrors, diverging lens and plane mirrors produce such images. So diverging lens, which is a concave lens, will produce a virtual image. Another thing is that virtual images are erect rather. That is the exact orientation in which the object is, the exact orientation, the exact direction where the object is facing is what you are going to get in the image. So for virtual images, you have something like this. The image formed, even though which you cannot see on the screen, is still going to be erect, still going to be in the same orientation or direction as the object is there. Virtual images are erect. Now let's discuss plane mirrors. So a plane mirror is a reflecting surface with one side coated. A plane reflecting surface. When we say that it's not circular, not spherical, not oval, not elliptical, a plane reflecting surface with one side of it coated, with one side of it coated. So, for example, we represent it as this. We represent the plane mirror as this. So this is the coated surface. This part that is shaded as the coated surface, while this part is the reflecting surface. The reflecting surface. So this is the mirror. You have the mirror here. Now, how about we look about the images, the characteristics of the images formed by the plane mirror? Of course, we can see one here, maybe one or two. We can see that it produces virtual image. So let's look at properties of um, let's say characteristics of images formed by plane mirror. Characteristics of images formed by plane mirrors. The imaging, the image, the image is number one, virtual, that is it cannot be got on the screen. If you bring a plane mirror here and you put an object in front of it and you have a screen here, you are not going to get an image of this object casted on the screen. So we say the image is virtual. You can only see it inside the mirror, that's behind the mirror. It cannot be casted on the screen. So we say the image is virtual. Another thing is that it is direct. Of course, if you put a pin or this marker in front of this mirror, you are going to see the image of this mirror or the image of this marker itself, the image of the object inside the mirror in this exact orientation. It's not going to be inverted like this. You are not going to get something like this inside the mirror. No. It will still be the exact orientation as this. Another thing is it has the same size as object. It has the same size as the object. So it's not going to magnify or diminish the image of the object. So if there is something of this height, let's say the height or the length of this object is 2 centimeters. When you check the image formed on the screen also, you are going to find out that the image formed, the image formed in the mirror, behind the mirror, will also be 2 centimeters. That will mean that it has the same size as object, same distance, from mirror, same distance from mirror as object. That is, you are going to have, if you measure the distance from this mirror to the image formed behind it in a plane mirror, let's say it is x centimeter. By the time you measure the distance between this mirror and the object, you will find out that this is also x centimeter. So that means the distance between the object and the mirror is the same thing as the distance between the image formed and the mirror in this case. So, characteristics of images formed by plane mirrors are that the image is virtual, that is cannot be caught on the screen. It is formed behind the mirror. Direct, that is the orientation remains the same, just as the object. Same size as object, same distance from mirror as object. Now, let's talk about the inclination of mirrors, of two or more mirrors, or two mirrors. Images formed by inclined mirrors. Images formed by inclined mirrors. In the next video, we will do a short demonstration of this particular concept. Images formed by inclined mirrors. When two mirrors are inclined at an angle, say theta, at an angle theta degree, to each other, the number of angle formed, the number of images formed rather, the number of images formed is n equals to 360 over theta degree minus 1, where n is the number of images formed, and theta degree is the angle between the two mirrors, angle between the two mirrors. So it's obvious that we can say that the number of images largely depends on the angle of inclination between the two mirrors. So what determines the number of images that will be formed is actually dependent on the angle between the mirrors. And looking at it carefully, we can say there is an inverse relation between them, an indirect relation. That would mean that the larger the angle is, the smaller the number of images we are going to have. So let's take a few examples. Let's take a few examples. Two mirrors are inclined at right angles, to each other. What is the number of images formed? Your guess is as good as mine. What do you think the answer is? What is the number of images formed? So to do this, let's write down our parameters, the things we are given and those things which we do not have. So looking at the questions, we have two mirrors. They are inclined at right angles. Right angle, that's 90 degrees. So we have our theta to be 90 degrees. What is the number of images formed? At least we have to look for n. Using this formula here, we have that n, the number of images formed, is 360 divided by theta minus 1. So that's 360 degree over 90 minus 1. And that's 360 divided by 90 is 4. You know 9 times 4 is 36. So you have 4 minus 1, which is equal to 3. So the number of images formed by those two mirrors is 3. Number of images formed is equal to 3. So 3 images to be observed behind the mirrors, in the mirrors. Let's take the second example with a different term. The number of images formed by two mirrors inclined to each other at an angle alpha is 10. Let's pick 5 because I have no calculator handy there. Is 5? Is 5. What is the angle of inclination of the mirrors? What is the angle of inclination of the mirrors? So let's undo this together. So the question says the number of images formed by two mirrors inclined to each other at an angle alpha is 5. That is, we have n equals to 5. Do you quite understand what the question says? Let's look at it again. It says that the number of images formed by two mirrors, forget all of this story. The number of images formed by two mirrors inclined to each other at an angle alpha is 5. That is, the number of images formed is 5. The angle is what we don't know, that is coordinate alpha. So we have n to be equal to 5, while the unknown angle is what we are looking for. This theta can actually be anything. Can be represented by x, can be represented by alpha, by beta, by gamma, by any symbol we so choose for the angle. So we know that n is 360 over alpha minus 1, where alpha is the angle, as the case may be. We have n, so that's 5 equals to 360 over alpha minus 1. So this is 5 plus 1. When we carry minus negative 1 to the other side, equals to 360 over alpha. We have 6 equals 360 over alpha. Then when we cross multiply, we have 6 alpha equals 360. And alpha is 360 degree over 6, which is 60 degree. That will mean that the two mirrors, which we have in this case, in this scenario, in this question, are inclined at an angle of 60 degrees to each other for 5 images to be formed. That being said, let's go to, let's see applications of plane mirrors in real life. Applications of plane mirrors. Applications of plane mirrors. Where are plane mirrors used? Plane mirrors are used in the kaleidoscope. They are used in the periscope. Yeah, what else? So let's take those two for now. Away from that, we'll go to curved mirrors. We'll go to curved mirrors now. We'll go to curved mirrors. Curved mirrors. For curved mirrors, they are those reflecting surfaces, reflecting mirrors that are spherical in nature. So we have two types. We have convex mirrors, and then we have concave mirrors. There are other types. We have parabolic. Sorry, yes, we have parabolic mirrors. We have parabolic mirrors. Parabolic mirrors. So let's pick them one after the other. Let's start with concave. Concave mirrors. Concave mirrors. For a concave mirror, the outside of this spherical mirror is coated while it's reflecting surfaces on the inside. While its reflecting surface is on the inside. So in diagram, this is what we mean. This is the cross section of the concave mirror. The cross section of the concave mirror. So we have this outer part. This outer part, the part that bulges outward. That is the reflecting. That is the coated surface. The coated surface. This part is non-reflecting. But the inside of this mirror here is a reflecting surface. Reflecting surface. So what we have here is a concave mirror. All we have here is a concave mirror. All we have here is a concave mirror. Number 2 is convex mirror. Convex mirrors. For convex mirrors, the outside of the mirror, the outer part of the mirror, is the reflecting surface. That's unlike this. It's the reflecting surface. While the inner is the coated surface. The non-reflecting surface is the coated surface. So that looks like this. We have this part coated instead. So this is the coated surface, the inward part, the coated surface, and the outer part is the reflecting surface. The reflecting surface. Note that the concave mirror is also called the converging mirror, while the convex mirror is also called the diverging mirror. How are those nomenclatures? Nothing for them is that a concave mirror actually brings incident light rays. Light rays is netted on it to a focus. It converges them. It causes them to meet at a point. While for convex mirrors, it spreads them apart, so they diverge. So let's focus on those two for now before we go to parabolic mirrors. There is more to both of them. Now, images formed by curved mirrors. So we take concave mirrors as a case study. Images formed by curved mirrors. For concave mirrors, let's start from concave mirrors. First of all, we'll label the concave mirror, then we'll try to explain some of the concepts that are attached to it. So we have a concave mirror, the outside part is coated. So this part we have capital letter P, somewhere here we have F. We'll be seeing what all of this means soon. We have C here. So we have P. P is called the pole. F is called the focus. C is called the center of curvature. PC is called the principal axis. The length PC, principal axis. So we have P as the pole, we have P as the pole, we have F as the focus, C as the center of curvature. PC, the length PC, so let's put something here. The length PC is known as the radius of curvature. The radius of curvature. Line PC, this line itself, a line drawn from P to C, is called the principal axis. And let's explain what each of them and others mean. So the pole, let's explain what the pole is. The pole is the center of the sphere from which this mirror is cut from. The center of this mirror, the center of the sphere of which this mirror is part. If this is the sphere, you cut out this part. You cut out this part that we have coated on the surface. So the middle of this sphere here, from which the mirror is cut, is the center. Let's call this.